So divide and conquer week. So what questions do you have? I posted a video earlier. I think Christina had asked a question in the forum about on 179 how that works. The other petition that we did, not the Limudo. I think it's quick select, but not 100% sure. Okay, it's saying my internet connection's unstable, so if I go away, that's it. I'll try to restart and come back if I do. That's a good sign. So anyway, that's the one that kind of works.
Hey,
from
David, I do have a question on that one.
Okay. Go ahead. Can you hear?
Yeah. So on the quick sort, are you always using like in the example of the book, you're trying to get lower than 5 on the left-hand side and larger than 5 on the right-hand side. So you're still using the 5 the whole time until you get that separation point.
Right. Well, you use whatever's the first position. In that example, it happened to be a 5.
Okay.
But yeah, that's what.
So what happens when they are like even? So like in the example, for example, like you have an X and an E,
right? But
the E would be the same as the E, but the X is higher. So they do flip flop.
Right. Yeah. If it's the same, I think I have to look at the algorithm. I think it goes with less than if it's the same. So it's going to go, it's looking for bigger than, not equal to. So it would skip the equal. So when you're moving your eye over.
Okay. And then when so the separation, or that S point happens when I and J flip flop.
Yes. It's the last J in essence. Or it's the last I before the flip flop. Okay. And I think in my video, now that I think about it, I was saying that go from the end position, and you don't. You go from the pivot both times. So I think in my video, I had that confused. But
can you say that one more time?
In the video, I was looking at comparing it from the right to the number on the right, and that's not correct. It's always to 5. So you're looking for things that are smaller than 5. And when you're going with the I, you're looking for things that are bigger than 5.
Okay. I think in my homework, I mean, like I have it like the I and the J moving.
Right.
But I didn't get to like the amount of levels that like they did in the book. But I eventually like get there. I think my concern was just trying to figure out that L and R and that S position, like how to do that tree.
Yeah, the S, they don't really make that very clear.
No, they
don't. S
is
a split point. S is the point at which everything to the right is greater than the pivot. And that's where you switch the pivot to.
It's the one that becomes the new pivot, right? Or trades with the pivot.
Yeah, it trades with the pivot.
Okay. So I had noticed that how you said like in the video, like at first you did say that, right? But then you pretty quickly changed over and said with the pivot.
Good.
Yeah. And then but one thing that you said that was just now was different from the algorithm did say greater than or equal to, less than or equal to. So that was how Christina mentioned the E in the example one. Right. It did say equal to.
Okay, on both ways? That seems weird. It seems like you'd have to pick.
Yeah, so either way, if you hit the one that's equal to, like if you hit one that's equal to, you would stop.
Gotcha. Okay.
So that would become the new, you know, if you were going from the right, that would be the new G, from the left, that would be the new R.
Right. I wonder if you had a lot of repeats, that would probably get ugly, but I don't know.
Well,
but
and
then
one
once you hit them, they would be in order and it wouldn't matter.
Yeah, it's true. You're correct. It would go right by. Yeah, you're right.
and see, one of the problems I was having is after you get like EEA,
Mhm.
like M, P, L, and X are all greater. So
Right.
like I wasn't sure what to do.
Well, it's recursive, right? Then you work on that other part later.
Okay.
Okay, let me share the screen on that page.
So do you just start with where it needs to be sorted?
You start with what?
And
You broke up there.
oh, sorry. Do you just start from where the next place it needs to be sorted? So
Yeah.
like M would be the new pivot for that end.
Let's pop this up here so you can see that here. Oh, went too far. Yeah, so in this case, you start with the whole range, right? And you're going to move over and you keep moving over till you find something bigger than 5, which happens there at that position. Then you move the J over till you get something smaller than 5, which is there. Okay. Then you flip those. You're still not done with this partition. So then you keep going down till you get to here. Here is where you've divided everything up. Okay. And you've got your J and I have flipped. Okay. So that at this point, S is equal to 4, and you're going to flop this 2 and this 5. Okay. And that would end the quick select, I think it's called. It's whatever that, I keep forgetting, whatever that other, not Lamuto, the other partition.
The Hoare partition.
The what?
The algorithm is called a Hoare partition.
Okay, gotcha. Yeah. At this point, you're done with that, right? That's done for this round. But quick sort is trying to sort. So it's going to keep recursively doing the 2 halves. Okay, so if you look at the algorithm itself up here, you're going to see this. Okay, that's the partition. That's not what we want. Quick sort is what we want. Yeah, I need to call it the Hoare partition. Okay, right here with the quick sort. Okay, so it's called quick sort from left to right. But if the L is less than R, okay, so you haven't flipped over yet, you're going to start by partitioning from L to R, and then you do the quick sort again on each half. Okay, and until you don't have any more to flip. Okay, so that means once you do this and you're done, you now do first this half and then this half. Okay,
What happens to the 5 in the middle? How do you know that that stays there?
Because we know everything to the left of it is less than, and everything
okay.
to the right is greater. Okay, so and it does it all on this side, but really, well, no, I guess it would, because think of the recursive call. You call to this at this point, it does the partition, it finds the S, okay, which is 5, or which is 4 at the position. It then calls this recursive call, and this stops, okay, and it's going to go on this left, okay, when it gets down to here, and this is partitioned, okay, then it's going to call this one on the left, and only when that comes back does it call it on the right here, and then the right again, and then when this comes back, only then does it come down and do this half. It kind of leaves that hanging out there, okay, because of the fact that it's going to open this one for this first version of quicksort that you open, and then it's going to do that again for the second version of the recursive call, all the way till you've gone left all that you can go. Okay, then it's going to come back and do the right ones. Okay, so the last thing it does is that right half of your original half may not be there, the right section of that. Okay, so this will always be done after all this is done. Okay.
So David, on our homework, I mean, should we have like that many lines, or can you like show, or should it be like traced out like that?
Yeah, it should be more or less like this. Yeah, if you want to really get it 100% correct.
Okay.
I don't think there's too much repeat there. because this shows the initial position, this shows there, this shows the switch. Now you wouldn't have to show that you move I to here, then you move it to here. You don't have to show that. I mean, you can go just to where it stops. And same thing
Okay.
on here. But yeah, I think those are all important. Okay. Other questions from 5.1? We kind of moved to 5.2, but
For that second part of the question, to draw the tree out, do you
yes.
go back and draw that tree that was on section B there?
Yeah. And you start from here, then the next thing that's going to happen is this one. Okay. And then the left and right are just showing, in this case, we're going from 0 to 3. So that's there. And then when you solve that, you know that the S is 1. You then go to this one. So this is the third one that you do. Okay. And then you go back to here and go to here. And then from here to there. And then back to there. And then gonna,
On that tree right there, sometimes it just leaves one out and doesn't mention how it got split out. Is it okay to, like for example, the 4, like in the position 3, it
Right.
just, it's the same like most of the way down there, but then it gets split off like at the very end. What happens if the one that is the same is the pivot? Does it immediately get split off? I don't know if that makes sense.
I'm trying to think of how that would happen. So you're saying if the pivot's a repeat, basically.
Yeah, so I mean, I guess the example is where it has the L equals 0 or the R equals 0 is one of them that does that.
Right.
And then like the L equals 5, R equals 5, when it does that, how do you know when you can go ahead and split it off? Does it have to already have been like, is it when you get one that switches with the pivot? Because that's not necessarily the case, right?
Well, yeah, I mean, if you follow the algorithm pretty slavishly,
Yeah.
it should work that out. The first thing you can do is calculate the S, right? Wherever that
Mhm.
falls. Okay. And then you're going to do each half separately and keep doing those partitions. Okay. So I think that's going to fall out. Then if the partition, you're just looking at whatever it is, the greater than or equal to, less than or equal to, which is very interesting. That all works out. But this is going to do the partitioning and find the split for you. And that J is the split here when it does the IJ stuff. So I'm not sure if that answers your question or not. I'm not 100% sure where there could be an issue. I will say, as far as test goes, I'm unlikely to give you the tree. Okay. Doing something like A, I think that makes sense. Doing the tree, no, that can get confusing.
I think I could do the chart, but the tree like totally throws me off.
The tree's confusing, yeah. So yeah, I wouldn't ask you to do the tree. Just the chart would be enough.
So on the homework, you mean you want us to just do the chart?
No, for test.
Oh,
For
okay.
the tree, do the chart. Or for the homework, do the
Okay.
tree, sorry. But on a test, I wouldn't ask you to do that. Homework's always harder than tests, right? Yep.
We hope.
Yep. You have time, you have
So why
resources. You can phone a friend.
Is it a typo on the bottom row of that tree? When it says R equals 2, R equals 1, should that be 2?
That's where it's flopped, I think.
But I thought you didn't have to say that. It would just be like, because you already had the split position at 1 above that, like 2 rows above it.
Yeah, so let's see where we were. So let's follow this down. So we had the whole thing here at this top one, and then we did the 0 to 3, which we're doing right here. Okay.
Mhm.
And then when we got this one done, we were at this point. Okay, why am I telling you? We were here. Okay, so that left just had 1. Okay, which left us with the 3, 4 here. Okay, which starts at 2 to 3. Okay, so from here, it's going to take 3 with a pivot of 4. And I guess that comes from you keep going as long as you have any elements at all. Okay, because these could potentially be in the wrong order. I don't think they could be the wrong order, but we'll just for the sake of argument. Okay. So when we do the I and J, they're going to flop immediately. Okay. Which gets us to, that should be 2, 2. You're correct. I had to figure out what you were saying, but that is correct. That should be, no, should be 3, 3.
Equals 2.
Okay, where we are. Okay, let me see. This is the 2, 3. This one is
Yeah.
3. There is nothing to the left of that.
Yeah, because the 3 is in position 2 and the 4 is in
Oh yeah,
position
it is a
3.
3. They did a separate line up here, but they didn't down here, which is weird. Yeah, that should be 2, 2. You're correct. I see what you're saying. And this one is 3, 3, which is correct. It should be 2, 2. Yes, all that to say, yes, you're correct. It should be a 2, 2.
Okay.
In fact, all of the end nodes, all the leaf nodes have the same number, right? Because they're only 1. You keep going, you have just 1. So it's 0, 0 here. It's 2, 2 there, 3, 3, 5, 5, and 7, 7. Okay. And there's no 4, 4 because the original split was at 4, but there'll be everything else. Okay. Because
So the split positions obviously couldn't be a leaf because they're like the parent of the 2 splitting down.
right. But every other position should be at a leaf node, except
Right.
except S. Okay. What other questions do you have?
Can
I've
you
got a
go
question
over,
for-
sorry,
Can we go back to 5.1 and do 2A? Talk about
Sure.
that one.
5.1, 2A. Okay, so 2A is an example of an algorithm that's not going to be particularly efficient. Okay, there's an easier way to do this. The way to do this is what I would call the king of the hill algorithm, where you just set the largest equal to the first and check to see if each one's bigger. You can do bigger and smaller at the same time, and it's a piece of cake. It does it in N. Okay, but this one they want you to do a divide and conquer. Okay, so the idea here is very much like quicksort. Okay, you're going to start by dividing in half, and keep dividing in half, keep making recursive calls until you get down to just 1 or 2 elements. If you're down to 1 element, then that element is both the largest and the smallest of that one array. If not, then just compare those 2 and return that. Okay, so that's going to look, 2A looks like quicksort, except that you're not sorting, you're doing, and there's no merging at the end. No, not quicksort, sorry, merge sort. Scratch that. 2A looks like merge sort. Okay, except you don't have to merge, but you are going to split it up and split it up all the way until you get either 1s or 2s, and then you're going to combine them back in that way.
So David, on that one,
Mhm.
would you initially set like a minimum and a maximum value and then search for it in each of the halves until you get down and then compare the 2?
Well, min and max get returned from the function, but you're on basically the right track. You don't set one initially. You leave that, you defer that until you get to the final call. You only set that at like at when you're down to 1 or 2 nodes left, and then that flows back where you compare it to whatever the previous one was. Okay, so if you had 1 subarray with 2 elements, 1 and 2, and 1 with 2 elements, 3 and 4. Okay, then when it goes to then the smallest of the first one is 1, the smallest of the second one is 3. When you combine those back together one more time, you would pick whichever one of those is really the smallest. So the smallest would be 1. Okay, so again, it looks very much like merge sort.
So you actually just like sort them, and because when you get to the end, they're sorted numerically, then that's when you can find like your minimum and maximum values.
No, that's the
No.
wrong way to think about it. You're not sorting it, you're grouping it and returning the smallest and largest. Okay. So
Okay,
um
sorry, I'm totally,
it's okay. Let me get, I think Excel may be the way to go. So let me share that. Okay, so again, you're looking for largest, smallest. Then whatever your numbers are. Okay, so basically you would start by splitting this in half. Okay, so you would get over here the three, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'll do 4 over here. Not there. Over here, I'm gonna do the 4, the 7, the 9, the 1. Okay, that's the first call. Then that's not equal to 1 or 2, so you break it up again with 2 more recursive calls. Okay, so you get a 3 and a 7 over there. You get a 2 and a 9 over there. You still haven't done anything with the max and the min. You get a 4 and a 7 there. You get a 9 and a 1 over here. Okay. Now this call would return the 3 as the min, or the smallest min value, and 7 is the max. Okay. This would return 2 as the min, 9 is the max. And they happen to be sorted, but they don't have to be. Okay. So
okay,
this would then, when we're putting them back together, this would give me the 3 versus the 2. So the 2 would be the min, and the 7 versus the 9, then the 9 would be the max for all this. Okay. And then over here, the same thing. We've got the min over here 4, the min's there, min over here is 1. So the smallest min is going to be 1. Okay. And then the max here is 7, the max there is 9. So then we're going to, 9's going to be the max there. Okay. I now compare to get for the whole thing that the min on this side was 2, the min on this side was 1. So 1 is the min for the whole thing. And there's a 9 both times. So 9 is the max. And that's the min and max. Don't know why that went away. There it is. That's the min and max for all this. Okay. So that's kind of how you break it down.
okay. And believe it or not, David, I actually have it written down exactly like that in my notebook because I just used an example, but okay.
How strict are you? I don't want to say strict, but like the pseudocode is what's killing me. Like I completely understand that. But like,
Yeah, me too, Kim.
I'm having the worst time. Like
Putting it into pseudocode that makes like
yes,
sense without just writing it out in English.
like I hate all the pseudocode in this book because I don't feel like I can follow a lot of it.
Yep.
Because it's not real code, and
It's not.
and so it's really frustrating.
If
Like,
it's
why
clear
didn't they
what
just
you're
pick a
doing-
language and just do it?
I understand. If you're clear, if it's clear what you're doing, you shouldn't have a problem. So if your symbols aren't exactly correct, it'll be okay.
I mean, like like I think on the last homework, I don't remember what problem it was, but it was something, and I was just like, I think it was the last one I had to do, and I was so frustrated. I just sort of put something, and I was like, I don't even know. Like, I think I even wrote, I don't really know how the pseudocode goes, but this is how you do it.
I did the exact same thing, Kim.
So
There was one that I was like, I have no idea how to phrase this. I know what it's supposed to do, but I don't know how to phrase it.
Yeah, if when in doubt, put it in whatever words you have. If it's clear, you'll get most of the points.
okay,
That's how that works.
because it's, I don't know. This doesn't really, I hate how the arrows point left. I hate, I don't know. I just don't like it.
I'm right there with you, Kim.
I
Like
know.
I'm so right there with you.
Like the very first homework assignment, and one of the things was like write in pseudocode. I went and did it in Python.
Yeah, I remember
I'm like, I could do this all day.
that.
But the other stuff, ugh, it's annoying.
We're being more mathematical. That's what it is.
Well, I wanted to ask about the merge, for problem 7, the stable sorting algorithm.
Yes.
It's been a few days since I watched the video, and I think you talked about it in the video, but I don't quite remember.
Yeah, I think I just mentioned it relatively briefly. So a stable sorting algorithm simply means that if you have two elements, so in our example, you have two E's, right? You'll put a tick mark on the first E, one tick mark there, and two tick marks on the second E. You go through the algorithm, and if the one E is still before, if the E with one tick is still before the E with two ticks, then it's stable.
Okay.
And that's all.
Yeah, I remember that now.
Yeah, it's what you're looking to see if you're in a computer situation where moving things around is computationally expensive, then you're seeing a stable algorithm is more efficient because it doesn't have to move things around if they're in the same position, if they're the equal. So that's all that was. And I would base that on the answer before it. If you do this merge sort, you can track this first E versus this last E. So does this E move over? That's what AEE when you're done. Is that first E in the AEE that first E of the example? If it is, then it's a stable algorithm. If it gets switched around, then it's not. Okay, and that's what you're looking at.
Which I have a quick question about the merge sort one. So I know it's an odd number. The smaller one goes first, like 3 letters first, and then 4 letters after that.
Mm-hmm.
And then when you separate the 3 letters, does it matter like which one is by itself and which 2 are together?
Yeah, well, the algorithm's going to do
EX
whatever the algorithm does. I think it takes the floor, right? So it would do an E then an XA. I think that's how it would do it.
Okay, that's what I have so far.
Yep.
And then
it's a
when
floor every time.
when the XA is separated and they come back together, they merge back together.
Mhm.
Does it merge? I guess EAX. Sorry.
No, it would merge back as AEX. Because you would
Okay,
have
so-
E in one, you'd have the AX. You would have sorted the AX first. And then it looks at
Okay.
what's at the beginning there. The A's at the beginning, so that moves over first. Then you have the EX, the E would move, then the X.
Okay.
So those are like lines that are each are sorted and you take whichever one. And remember, one goes empty, you just move the whole other one over in one shot.
When it has an odd number of letters like that, because the example in the book had an even number, and the example, the word we have to do has an odd number. Does it matter how many you do in the, like, do you do fewer in the first and more in the second, or does it matter? Like, I have 4.
If you're following the algorithm, but the algorithm has the floor of n divided by 2. So you're going to take the lower number.
So go low, the lower one would be
Yeah.
first.
Now, if you change, I mean, the
Okay.
floor is that little, little L's, little brackets with only the bottoms on them for the floor. If it were just the tops, it'd be the ceiling, in which case you take the higher number. Okay, so the algorithm tells you which way to go. Is it the end of the world if you get that wrong? Not the end of the world. But to be precise, that's what those numbers are. I'm not sure if those are familiar numbers to people or not, but that's the floor and the ceiling. So, I'm talking about, again, if it's an L, there's a line, it's like a square bracket with the top missing. Okay, that's going to be your floor function, which takes the division and lops off the decimal portion. Doesn't round down, it just makes it down. If it's 2.1 or 2.9, it's just 2. The ceiling function is a square bracket with the bottom missing, and that's if it's 2.0001, it's going to go to 3. Okay, so anything greater than 2 becomes 3. So that's the floor and ceiling function. And that's why you don't have to decide which way to go. Okay. And on merge sort, it has this version of merge sort has floors in all those places. You could rewrite it with ceiling and it doesn't really make any difference.
Oh, I'm not seeing that.
In the algorithm?
Yeah,
It's merge sort. Which one is that in 5.1? Yeah.
yeah.
Page
72.
172.
Let's see, right here. See, that's saying the floor then divided by 2.
Oh,
The floor of those little,
I've never seen that, so I just read it as a
Okay.
bracket, I guess.
yeah, it's missing the top.
So
Okay.
do the lower number first.
The lower
if you
number.
have to split.
Yes.
Okay.
Yep.
Okay, that makes sense.
Okay, and then yeah. Sometimes I have to add 1 to make it work out the other way, but yeah, that should be okay on that one.
Okay.
Okay. Other questions about merge sort? In general, I think you'll find that merge sort is the most commonly used sort because it's more consistently accurate than quick sort. There are faster sorts somewhat, but not really much. Merge sort's a good sort. If you know merge sort, you're going to be okay. There's hardly ever not a time to use merge sort. Okay, so it's the best one we've seen so far. Okay. And then quick sort, the issue with quick sort, and the book talks about this, depending on how the partition number gets picked, affects greatly the efficiency. Because for divide and conquer to be maximized, you're going to divide it in half every time. And we know merge sort's going to divide it in half every time, right? Within 1. Quick sort could divide it very unevenly, depending on how the pivots get set. Okay. If you have the numbers 1 through 10 in an order, you pick the pivot 1, then there's nothing to sort, right? Everything it's in that position already. And it would take it a long time to figure that out. Okay, so the pivot really makes a difference on that. And there are other ways that we didn't talk about. I don't think I even mentioned in the video, but it is in the book that, they sometimes take the endpoints and the median value and get the average of those and make that the pivot to try to make things better. But there's still ways that the numbers could flow. When we do number examples, we do all numbers within, a fair range. In the real world, numbers sometimes are wildly different. Okay, so quick sort is more variable. It has much more of a worst case, best case than does merge sort. Okay. Other questions about quick sort, how that works? And again, it's important to remember that a partition is not a sort. Okay. A partition gives you all the values that are less than the pivot point, and all those greater than the pivot point. But within these two groups here, between this group and this group, you have no idea the order. All you know is they're less than p, but you don't know how they relate to each other. Okay.
I had a question on 5.3 on number 2,
Okay.
the leaf counter one.
Yes.
So just because it didn't say it, the leaves are just at the ends, right?
Yes.
Okay.
Yes. A leaf is defined as a node that has no children.
Okay. I just want to make sure I was right.
And if it's correct, you have to show that it's correct. If not, you have to make a correction. Spoiler alert, you need a correction.
Well, I was kind of thinking that because it's like it just calls itself. So it's like it doesn't really, does it even do anything?
It does. It'll work in general. It works almost all the time. Because what it's saying is how many, until you get to the end, if you're on this tree here, well, how many leaves are there? Where, well, there's this number of leaves plus that number of leaves. Well, how many are there here? Well, it's this plus this. So this comes back as having 1 leaf. Okay. And then this one's going to come back, and it's going to add it up correctly. Okay. The trouble for this one's going to come in if you have a single node. It's going to be incorrect. So I'll give you that hint as well. Okay. If you have a single node, then it's going to return a 0 for the number of leaves.
Oh, so if it has no branches, it's just 1. Okay.
And it should be 1. That's the error with that algorithm. Okay. Hopefully you didn't
So-
prove it to be correct. If so,
So if T is the tree,
it is.
so if the T is null, return 0.
Right. That's
Basically,
its
if there's
method.
right, if there's nothing there,
Yes.
but otherwise, so why wouldn't it return? Oh, because it doesn't have a left and right if it doesn't have any
Right.
branches coming off?
Yeah.
Okay.
Which will return 0 both times. If you have just one node, it's not equal to null, so it wouldn't return 0. So it would return the leaf counter of the left tree, which is null, so that returns 0. And the right tree also returns a 0, but it still has that 1. And that's
Okay.
what,
Because it just didn't seem like it really did anything. And so that was I was like, is it because it just calls itself?
no, it does
That's-
work. It will add them up.
Okay.
That else does do the additions. Other questions on 5.3? And again, in this
then-
chapter, in chapter 5, and if on the exam I mentioned specifically a divide and conquer algorithm, then what I'm looking for is something that divides in half every time, even if it doesn't make any sense to do it. Think of looking for the largest number in an array. It doesn't make sense to do it, but to do it with the king of the hill algorithm would be incorrect because that's not a divide and conquer algorithm. Okay, so on the test, make sure if I'm asking for a particular kind of algorithm that you give me that kind of algorithm, even if it's stupid. The book gives an example of multiplying numbers together with divide and conquer. It turns out to be worse than just doing it the normal way. Okay.
So for number 1, is it basically asking for the height to compute the height?
Yes.
It's the number of levels?
More or less, yeah.
Okay.
So just adding in those things that you're supposed to return, right?
Right. Okay. So section 5.4 is interesting. This whole multiplication stuff here, just it's not very intuitive. I don't think. I think you would think that if you're looking to maximize the efficiency of your program, doing multiplication seems like it's about as simple as it can be. But it turns out that it doesn't. It's not as efficient as it could be. And I think the reasons that it's not is interesting. And if you think about it hard enough, if you go into a dark room and meditate for several hours, you can get to the idea that it's because you're doing the same multiplication multiple times when you do it normally. And that's what this does. Okay. And if you understand how this works, then good for you. You're a smart person. If not, if you can just do it, that's okay too. Okay. But it's gaming the system. And again, for any kind of numbers we're likely to multiply, this is not worth the effort, right? We can multiply really big numbers in Python in mere seconds, okay? But as it says right here, the big thing here, cryptography, is where you're taking giant prime numbers multiplied by other giant prime numbers. If you have that much going on, then this can significantly increase the performance, okay? And if you teach high school math, this may make your kids excited. I have no idea what makes kids excited anymore. Probably a new video game and nothing else. But this as a kid, this would have fascinated me. But I was a weird kid, so you know how that goes. But yeah, it's interesting how it shows. I mean, mathematics is always a complex subject, right? It's once you set the rules, it's discovered rather than invented. Once you have the rules in place. This shows a little slippage to me there, right? It's a little thing we didn't anticipate. That's a result logically of those rules, those assumptions that we made when we started putting together our mathematical systems. So I find it very fascinating that we can gain some things here. But again, if you know those formulas and can do those results, that's all I care about from there. Okay. And I didn't do the matrix multiplication. It works on the same principle, but I figured that was enough to remember, so we won't go through that. But
So when we do that, that 4-digit one,
Uh-huh.
you split it in half and then split it in half again. So you're essentially doing it for each of those parts separately, right? And then putting them back together.
Yes. Yep.
So it's like it's like the thousands place and the hundreds place times the thousands place and the hundreds place.
Yep.
And then the tens and the ones.
Yep.
Separately. Okay, that's what I thought. I was making sure, because I kind of like set it up, but I haven't done the actual math on it yet. 'Cause I just want to make sure that was right first. Because I figured once you get everything in the right place, doing the math is easier than putting it in the places.
Yes. Makes sense. Yes.
Hey, David, a question on that one. I actually looked up like a video online of like how to do those.
Mhm.
And they had a much more condensed formula that I think like the book eventually gets to. That's like the A1 times B1, 10 to the n, and then plus A1, B0 plus A0, B1. Is it
Mhm.
okay to use that formula? Because when I looked, like you get the same answer either way, but this is a more direct formula.
Yeah, either way is fine. Doesn't matter to me.
Okay.
Yeah, either way is okay.
And then I have no clue how to do the number 1 on that one to tell.
Okay, so
I was gonna ask that too.
yeah, so
So I did that by doing like this, what's the smallest and largest to see what they got.
yes.
Like,
I mean, that's it. What's the smallest number with 3 digits?
yeah, well, I did it for 2, 3, and 4 to test it out. to
It's
get a
100,
formula.
right? That's the smallest number of 3 digits. Because if the 0 were anywhere else, it wouldn't be 3
Yeah.
digits. Okay. So you can generalize that. If you take the smallest number of 3 digits, 100, multiplied by the smallest number, again, that same number, 100 again, how many digits do you get? And that's kind of how you work it on that. Okay. And then on the other part, the largest number of digits, what's the biggest number that has 4 digits? 9999, right? So you can work that as well. Work that out to get the number of digits. Okay. And if you put them in that form, and it helps to convert that into exponential form rather than just keeping it, so you're for the n number of digits, try to do something to the n to get those things going. Okay. Which I think
Does it have to be
That's
that? Because mine was linear, not exponential.
what's that? You broke up.
Does it have to be exponential? Because mine was actually linear.
It doesn't have to be.
And the wording of it was so confusing though, because like why, I was trying to figure out, why does it say 2 decimal in digit integers? Does
Oh
that just
yeah,
mean
decimal
anything?
meaning base 10, not binary or not
Oh, okay.
something weird. Yeah.
Because I was like, does that mean like that they would have to have the same decimal? And finally, I just started working it with, that they had the same digits.
Yeah, no. Yeah, that's fine.
Okay.
But yeah, you can do those examples of you can do it in Excel, 3 digits, 4 digits, whatever, how many digits do you get? And generalize that in terms of n. It's going to be the easiest way to do that. Okay. Was that helpful? Christina, whoever asked that question?
Honestly, probably not. I think I'm just gonna have to like try it.
Yeah, do some examples. That's the best way.
So would you just take like the 100 and 9999
Yep.
and like multiply them and just see how many digits you get?
Yep.
Okay.
And you
So
should
let
see
me
a pattern.
let me ask a stupid question. Like, how do you know? I mean, is it when it says like multiplication of large numbers, do you automatically start with 2? I mean, like, do you start with 2 digits? I
Oh,
mean, I
you
guess
could.
That's what I did.
Yeah, it has to work for all digits. So even 1 digit, the smallest one digit number is 1 times 1, 1 digit, right? The biggest is 9 times 9, which is 2 digit. So
Okay.
whatever formula you get has to work for all those in terms of n. But it could be worse. I could have given you 3a. Look at that one. That's ugly. Okay, then the last section is closest pair and convex hull problems by divide and conquer. Okay. Unfortunately, I didn't see a problem that worked out real well for the convex hull. So there's no example of that. But you should look through the examples in the book because you could get a test question on those. And I talked about them on the video. We can talk about them again here in a second here. Okay. The one problem I gave you from this section is the closest pair problem in what, one dimension. So it's just a line. Okay. So that simplifies things a fair bit. Okay. So that's what you're trying to figure out. In the case where you're just on a number line, how do you figure out, how do you do this divide and conquer based on that? Okay. And you start by sorting your points and then breaking them in half and all that. You know, and then the question becomes, is it a good way to do it? Is part B of that. And you can think about that. But the general idea of how these work, and we did the convex or the closest pair problem before with the brute force, we were trying everything. Okay. And the idea here is that you just get this median point after you've sorted them. Okay. And then you get you check all the points in each half rather than all the points everywhere. So you never have to go from this point over to that point. Okay. You get the smallest point, the smallest closest pair on the left-hand side, that distance, the distance of the closest pair on the right-hand side. And then all you have to worry about is anything that's kind of in the gutter between those two sets. Okay. And making sure there's nothing closer. Like in the example here, these 2 points up here are going to probably be the closest. Okay. And you want to be checking those, and that's showing where that distance is. Okay. And again, you know that if D is the smallest of these two numbers here, then anything outside of here is going to be at least D from the other point. So you wouldn't have to check them. So that's kind of how that one works. Okay. And again, the homework's a simplified version of that. And then the convex hull problem is a little more complicated, but it's basically recursively doing this. Again, that when you divide all your points out, the furthest, the point with the smallest x value and the point with the greatest x value have to be extreme points. Again, think of where we had the nails in the board and you put the rubber band around them. Those 2 points are going to have to be touching the rubber bands. There's no way for anything less than that to cover them. So you know they're there. Okay. So you draw a line between those 2 extreme points, the lowest x and the biggest and the greatest x, and then divide it to upper hull, lower hull. And then for each half, you're going to look for the point that's furthest away from that line. Okay. The point that we call P max. That point also has to be an extreme point because there's no way anything that's closer could get to that. Okay. And then you just keep doing that recursively until you have all the points. Okay. So yeah, I think that's a decent enough algorithm to do. I don't think it's horribly difficult, but again, the homework examples weren't there. They were a lot more complicated than I wanted to give you for that, but do work through the homework example there. It does give us one, I think, or maybe it doesn't. It doesn't really give us one. So I guess I need to make up one at some point. But that's the basic idea. And again, you have to be thinking about this whole divide and conquer strategy. And that's how these problems start making more sense. Okay. So yeah, and just dealing with this first one with the one dimensional version, that's not a super difficult thing to come up with. So it's not too bad. Your D then becomes just a segment, not an area. Okay. So what other questions do you have about anything?
Could I
Hey, David.
possibly, sorry,
Could I possibly get you to go back to 5.4 unless someone else has something in 5.5 they want to talk about?
Yeah, we can always go back and share again. And share the screen.
I was just wondering if you could maybe do an example of the multiplying one of number 2. Like, I got halfway through it and then I think I lost myself.
Okay, let's see. So with this, okay, so with the 4-digit ones, you're going to go up here and get your formula here. And you're going to calculate these guys, right? Okay. And let's see, starts up somewhere else with the number of digits you have. Okay. So you do the C2 one first, okay, and then you do the C0 one, and then you do the C1. Okay. And again, if on those 4-digit numbers, you're going to have to take the first half and the second half and plug these in, okay? And then, because you're only dividing it into 2, you have to do it again. So let me do an example here. Go back to Excel, maybe.
Yeah, I got I did divide those. I gotta find where my notes are. Yeah, divided them into 2. So then you gotta break it down again and divide them into ones and keep going.
Yeah, so if you have, you have that times that, okay? Then your A1 or A0, the first time is 34 and your A1 is 54, okay? And then your B0 is 57 and your B1 is 86, okay? And then you can do your C2 is going to be equal to A1 times B1, okay? So C2 is going to be 54 times 86, okay? And then C0 is going to be A0 times B0, so it's going to be equal to 34 times 57. Okay. And then from that, you can get the C1, which is just a bunch of other stuff. We probably won't go through all that, but you're going to get a bunch of other. That's the A1 plus A0 times B1 plus B0 minus C2 plus C0. Okay. That's going to be all of that one. But this doesn't give you the answer yet. So you then would have to do a new round with the 54 times the 86, okay, where your A0 is 5 and your A1 is 4, and then your B0 is 8 and your B1 is 6, okay? And then you would get your C2 being equal to the 4 times 6, right? And then your C0 would be equal to 5 times 8. Okay, and then you get your C1 by that little formula they've got there. But at that point, when you're down to single digit multiplications, you don't have to break it up any further. You'd be done with that. Okay.
Okay, and then do you just add them all back together once you?
Yes.
Okay, so you do that 3 times essentially.
Yep.
And then add up your final answer.
Yes.
Okay, thank you.
Yep, that's how that works. Okay. Other questions?
Kim, he did not get to your code yet. I know you said you stepped away, but he did not explain that yet.
Yeah, what was
I
that?
was wondering. Yeah, I had to step away for a few minutes. So, so for on 5.5 for problem 1, like the closest pair. One question was, are we talking about on a number line again?
Yes.
Okay. And I was trying to look at the algorithm that they gave on page 194.
Uh-huh.
So, I mean, I guess it'd be kind of sort of loosely based on that.
It is.
But I didn't understand the like last third or so of the algorithm. Like, I understand where it's like basically dividing it into two arrays
Right.
and then finding the distance between the closest pair in each, and then finding the comparing those.
Right.
But then from there, I don't really understand what it's doing. Like, why
Okay,
is it-
so you're doing all this to just divide up your array, right?
right.
Into two. So you're taking the first half of P goes to P1, and the first half of Q goes to Q1. And that's because you have X and Y coordinates, right? Two-dimensional.
Right.
But in our example, we just have one of those. We'll just have two
Right.
lines instead of 4 lines. Okay. Once you've done that, you're basically going to say, run that again
Right, on
on
those.
the one-dimensional. So you can kind of start there. Okay.
Okay.
And you get the distance there is the closest 2 points that you have in the half of the number line that you're picking first. Okay.
Right.
And then you get the dr is the right half, the closest 2 points. Okay. Then you're going to set your d to be equal to whatever the smallest of those are. Okay. Then what you're worried about at that point, you're going to get the median. Okay. That's what the m is. Okay.
Okay.
And you have to look at all the points that are within d of that m. Okay. So whatever, if d is 3 and your m's at 5, you're going to look at the points between 8 and 2. Okay. Check those for the closest point. Okay.
But
The concern being that you may have points that are closer together, and the picture shows in here the 3 dimensions. See, these 2 points are closer together than anybody else, but you wouldn't know that. So you're checking the gutter. So that last part's checking the gutter.
Okay.
Okay. And D's, if it's further away than the median point than D, then it's already bigger than D. So you don't have to worry about it. Okay. But that's what that's checking.
So David, on the answer to the homework problem, is it basically just a good chunk of the algorithm that's already there in the book?
Yes.
Okay.
Just cut it down to and you don't have to do that. I mean, that one, I don't know that it asks for an algorithm, does it? Or does it tell you how to do it?
No, I think it asks for an algorithm.
Yeah, design algorithm. Yeah. And it says it's based on the one that it gives in the book. It's in 1 dimension, not 2. So you're just going to cut some of that out.
Okay.
So going back to 194, what exactly is like, so that makes sense what you're saying, but I still don't really follow what the code is saying to do. Like, so you find your median,
right?
That's the M, but then I'm just not following those next 2 lines and then the for loop exactly.
So what you're doing here, you're taking all the points, okay, that are closer than M, or sorry, closer than D to M, basically. Okay.
Okay.
You're creating a new array from that.
Okay.
Okay. And then what are we doing here? Good Lord, who knows what we're doing here? This is very confusing. We're getting a D squared. Okay. We're going, now where does num get set? Num is how many points that we have. So we're going to 1 less than that. We've got a K counter. This is just iterating through the points. I'm not sure why it's that complicated. And
the new array, like that's within the median.
Yeah. The new array is all the points that are in the gutter.
Okay.
And all that code is just iterating through those points and checking the distances. And that's all it's really doing. But it's ugly. I'm not sure why.
Yeah, I didn't understand. Like, that makes sense with the median thing, but it just looks so weird. I didn't understand.
It does really look weird. Yeah. I don't like this code stuff. I don't like it. Yeah, that one's just, and I'm not sure why it has to be that complicated. I'll think about that a little bit more. Yeah, I don't know. I come up with something, I'll post a video, but yeah, that seems more complicated than it needs to be just to take care of the gutter.
David, can I ask a general question?
Yep.
I am still very, 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 very hazy on the time efficiency. Like I understand the chart and like it's how many times that base case is like running. Like I understand
Right.
that.
Mhm.
But like on this algorithm, it says to determine the efficiency time. And like a lot of them ask that.
Mhm.
I just don't understand.
Mm-hmm.
I just don't understand that. Like I understand like if you run it one time that it's linear time. If you run it
Yes.
the base case twice, then it's n squared or whatever that is.
Right.
But I guess my question is, I'm afraid like on a midterm that if that question gets asked, I have no idea how to answer it.
Well, the things, if I ask on the midterm, I'll try to make it something that's straightforward. I will say that make sure that you remember that anything that divides things in half is at a log something. That's the half part. Okay, so log n or n log n, depending on what's happening. So, if I ask it on a test, it's probably going to be something pretty clear where there's 4 loops. There are 3 for loops, then it's n cubed, and little things like that, kind of the gut feel. And certainly be able to know which is more efficient, which is less efficient. Some of them get really complicated, and that was all the chapter 2 that we skipped. So I'm not going to hold you to any great standard on that. But yeah, most things we do are going to be some kind of a polynomial form, unless it's one of our divide and conquer, which is going to be a logarithmic form. And then anything like a combinatorics, when you got to do everything with everything, those are the exponentials, or the worst, the factorials. So.
Okay. And see, I kind of understand. I mean, I understand like the basics of that.
Right.
But I don't know. I just feel like I haven't gotten that yet. But what you said, I understand. Like that's the part of it I understand. I just feel like it's more complicated than that, and I'm missing it somewhere.
Well, I mean, that's because we skipped that section, right? We skipped that because that is pretty mathematical and requires that you remember stuff from calculus, which some people do and some people don't. So that's why we didn't do it. So we're left with the gut feel. Okay, so the gut feel, on those, make sure that, you go back and check your answers to make sure that you're getting those gut feelings. If you're like, oh, that feels like it's n cubed and it's like log n, then you're not understanding. But if you're understanding, and I try in the homework solutions to kind of reason about those rather than we don't do the recurrence relations or any of that stuff, even summations. So that's kind of what I'm thinking about.
Okay, thank you.
Okay. Other questions?
Can I ask you a question about the lesson plan assignment?
Yes.
So it says brute force versus decrease and conquer, but I have an idea for something, but I think it's more brute force versus divide and conquer.
That's one of the
Would you
options of
think
decrease.
it that way?
Yeah, because I mean,
Okay.
remember, decrease comes in varieties, right? And
Yeah.
the constant reduction is just divide and conquer. So divide and conquer is fine.
Okay.
It's a subclass of decrease and conquer.
Yeah, because I was trying to think of something where you could teach those terms to elementary students so that they could understand it.
Mhm.
And so I came up with an idea, but then I was debating myself on whether like it was more divide and conquer. But that was before, when I got the idea for it, it was before we started this chapter.
Right.
And so this question, and then once we started this, I was like, yeah, I'm pretty sure it's just divide. That my idea.
That's perfectly okay.
Okay.
Other questions? Okay, let's call it a night. I've got this recorded, so I'll go ahead and put it up hopefully tonight. If not, somebody send me an email tomorrow saying you forgot to put it up. I'm on spring break, so who knows what I'll do tomorrow. Could be anything. So anyway, yeah, if you have other questions, make sure you post them on the forum or whatever. And if I need to put up a video or whatever, I will certainly do that. Okay, so be another video on Sunday. We'll go on to the next chapter. It's got to be near midterm. We have 12 weeks. Is that right?
Mhm.
Okay, so there may be next week, maybe midterm week. I don't know. I'll look it up. It's probably on Moodle. I'll let you know certainly when I talk about the video. You know, there's things happen. You know how it is. Some of you are real planners. I'm more reactor. It's kind of how I work. So anyway, okay, you guys have a good weekend, and I'll see you next week.
Thank you.
Thank you.